right? Can I say that this Z approximately should be about a fourth of these neighbors? Is this a good prior model for something that's smooth? All right. So doesn't this look like sort of the, it looks like the model reduction thing we did before, right? Of course, we went from Z to Z, so it's not real model reduction, but there is a mapping, let's say Z equal to AZ. And the A matrix looks like that, but you can treat that every Z, except in the edges, is the average of the four neighbors. Now, this model is wrong, right? I mean, actually, if you take this matrix A and you form I minus A, all right, you will find that you cannot solve for Z from this model. All right, so this is certainly, it sounds nice that this is the average of the four neighbors, but this equation is not something you can solve with. So if you cannot do this, every model introduces error, and the error means you have to revise your model as Z equal AZ plus the uncertainty of this model, plus some noise. All right? I want basically to tell you how we got that prior in a different way that that the topic we discussed on Wednesday. So I want to smooth things, so I'm using Z equal to AZ, and because this obviously cannot stand mathematically, I am going to put some noise to it and say plus some uncertainty, the error that I'm doing in this model, right? Because obviously it's not the correct model. Yes, it smooths, but there is some uncertainty. And we're going to model R with, let's say, some Gaussian error. So will you agree with me that the prior of Z then is the distribution of the model error evaluated as Z minus AZ? You remember when we were discussing about the likelihood models, right? So, the prior on Z from this equation is really the distribution of R, but evaluated at Z minus AZ. Okay? And if you call Z minus AZ, so if you put R this Gaussian, and you call Z minus AZ L, then you get exactly the smoothing prior that we use in that interpolation problem. In the notes on Wednesday, I left it, I said you do a transformation and this and that. I did not elaborate on this because we did not discuss this context of how this additive noise comes. But here is a very nice way of deriving it. Okay? So again, you smooth things. You can do this actually with images, with voice, lots of functions, that they are smooth. But then because you smooth it, you say I introduce some uncertainty in this model. You make this distribution of R to be Gaussian with some noise, which maybe is not known. And the prior model then from Z from this equation is this Gaussian of the model error evaluated at 1 minus A times Z. And that gives you a smoothing prior that is what you see there. And this, we use it to do interpolation only from the prior, but later on, if you use a likelihood model and a prior like that, basically you can come up with much more realistic ways for doing regression problems, and we will discuss this a few lectures down the road. All right. Okay, I need to finish the lecture today with a little bit of more metrics calculations for what is called Gaussian linear models. Okay, and this is something you are going to use about 1,000 times if you work in this area. So these are formulas, you need to have them ready to look at and be sure you know how to use them. So let's say the following, that these are all vectors, x and y. So you have a model that you have probability for the probability of x given by this Gaussian. and the probability of y given x is given by this form, and we call this Gaussian linear models because the mean of y given x is linear in x. All right? But the covariance has no x dependence. This is very important. If you put an x dependence there, then none of these equations is valid. So the mean is linear in x, all right? And this is x independent. So what is interesting calculation, and it comes all the time, is if you have something like that, you want to invert this calculation and using Bayes' rule, compute the probability of x given y and compute the marginal of y. And you can see, for example, why how Bayes' rule will come, right? Because if you take the joint distribution of x and y, you can write as p of x times this, or you can also write as p of y times p of x given y. So from there, you can compute from these two entities, you can compute those two entities. Okay. The calculation actually, it's straightforward, and it's application of the trick we discussed on Wednesday, which we call it what? Complete the what? The square, all right? And I can tell you, if you don't do these calculations once by hand, next time you're going to have to deal with this in your own problem with much more complicated distributions. You won't be able to do it right. Okay? So completing the square, it's, you know, it's a weird terminology, but in statistics it works. Okay? So this is what we're given, all right? And we need to reverse these basic calculations here, p of y and p of x and y. So the starting point, and I'm not going to give you all the algebra, maybe I will highlight some of the calculations. So the starting point is to form the joint distribution of x and y given this marginal and this conditional. So let's call z x and y, and we need the joint distribution of x and y. Of course, you know the joint distribution is p of x times p of y given x. So if you take logs, you get this nice expression. Log of p of x is this. And I only keep the exponential terms here because that's where the action is with the x and the y's. And that's why I put a constant. And the log of y given x from here is this nice expression. So if I ask you to compute the probability of x given y, let's see actually what is next, and then I will ask you. So let me see. Well, actually, okay, so before I ask you, so from here, will you be able, if I ask you to compute the probability, the Gaussian, the joint Gaussian for x and y, how would you be able to, from here, to write the Gaussian for the probability of x and y together? What are you going to have to do, actually? Actually, it is a completing the square as well, right? So what will you have to do to write, to identify what the mean and the variance for x and y is? We're going to have to write it in quadratic form in a similar fashion to what actually you see here. This one quadratic, this one quadratic. But rather than having x here or y there, we're going to have a vector here, which is what? X and y minus some mean, and then here some matrix and another x and y and that mean. And how do you do this? By rearranging this equation. All right? You can write it like this. So this is only the quadratic terms. So will you agree with me that the variance, the covariance of x and y is the inverse of that? I mean, if you do that, you know, put this together, you get that. So this better be sigma minus 1, right? For the joint distribution. So the covariance of z has to be equal to the inverse of this matrix. Correct? And what have I done to go from this inverse of this factorized matrix to that? I used this matrix inversion lemma. And what was the name coming under this nice lemma? That you need to remember because it's it's fundamental to machine learning. What's the name going with